we want to start looking at the maxima and minima of multivariate functions, wherein much of what we will discuss mimics exactly what was done in the single variable case. We'll start with the definition of local maxima and minima, which is exactly the same as the single variable definition, but with vectors as our inputs. As usual, you're a local maximum if you're bigger than everything nearby, and a local minimum if you're smaller than everything nearby. We change this to a global max or min if you're bigger or smaller than everything in the domain, respectively. As a quick example, the function x squared plus y squared is the two-dimensional analog of a parabola. Here, the point 0, 0 is a global minimum, since if you evaluate f at this point, you will get 0. And as the output is the sum of two non-negative numbers, the result of f will always be non-negative itself. Now, in single variable calculus, we used the roots of the derivative, called critical points, to help us find extrema. The same will be true for multivariate functions. Thus, if f is a C1 function of n variables, we say that a point C is a critical point if its gradient is equal to 0. Here we're really seeing that the gradient is playing the role of the multivariate derivative. Also note that this here is the 0 vector, since that's the only thing that could make sense. Now, as much as things seem to be similar to the one-dimensional case, finding critical points for functions of more than one variable is much more complicated. Case in point, here's a polynomial. Let's find its critical points. Following our definition above, we compute the gradient and set it equal to 0. Being a polynomial, the partial derivatives aren't too bad to work out. This ends up giving us a non-linear system of equations. The first equation comes from setting the x partial to 0, while the second equation comes from setting the y partial to 0. And there are some extraneous factors here, so let's simplify a bit. So we have to solve this nonlinear system. There are a bunch of ways that we could do this, but I'm going to use the second equation to write y is equal to 2x. Plugging that back into the first equation, we get the following polynomial, which now depends only on x. Factoring, we get x is equal to -2, 0, and 4. That's only half the solution though, since we need the y values as well. But we know that y is equal to 2x, so that gives us 3 solutions in total: -2, -4, 0, 0, and 4, 8. Okay, so having 3 critical points isn't that weird, but it turns out that some functions can actually admit infinite critical sets. For example, let's take a look at the function f of xy equals x squared y squared. Same as before, we'll compute the gradient, and we'll set it to the 0 vector. In computing the gradient, we get 2xy squared and 2x squared y. Again, this gives us a system of equations that we can simplify a bit. And if you stare at this, one of x or y has to be 0, though it's not necessary that they both be 0. That means that we have an infinite number of critical points. The set of all points where x is 0, and the set of all points where y is 0. So the whole point of doing this is that the same theorem we studied in one-variable calculus is true here as well. If f is a C1 function of n variables, and c is a max or min of f, then the gradient of f at c is 0. That is, c is a critical point of f. This gives us our strategy: compute the critical points, and check whether or not they are maxima or minima. But just like one-variable calculus, this is a necessary condition and not a sufficient condition. That is, every extremum is a critical point, but not every critical point is an extremum. The example we used before was the function x cubed, which we know has a critical point at x equals 0, but is neither a maximum nor a minimum there. The example I'll use to demonstrate this in multiple dimensions is particularly interesting. Let's look at the function x squared minus y squared. The gradient is 2x negative 2y, so that 0, 0 is a critical point with associated value f of 0, 0 equals 0. However, looking at the points x0, we see that it's easy to get numbers which are bigger than 0. And conversely, 0y will always be less than or equal to 0. Since there are points nearby which are both bigger and smaller than 0, this can't possibly be a maximum or a minimum. So this has all been a good start to our optimization process, though we'll have to study a few more things before we can classify critical points.